Hi everyone. In this lesson, we will implement the van der Pol equation, which is nonlinear, on the what? On the unscented Kalman filter implementation. Okay? And so, first of all, we need to give the parameters, just like this one. Parameters. And so, first of all, we need to give the... No, I'm sorry. Time. Parameter. Okay, so the dt, for example, 10 milliseconds. This is the time step, and total time 20. Okay, total time, and also time vector can be built with the what 0 with the time step of the dt and up to t. Okay, this is the time vector. So for the van der Pol parameter, we need to give the mu value 1.0. Okay, and also initial true state variable x true is equals to 2 and 0. Okay, the first parameter describes the position, and the other one is the velocity. Okay, velocity. After that, we need to define the process and measurement noise covariance, because if we want to create some random values as a noise, or we need to define it, and so we need to update the whole UKF code based on the what? Based on these parameters. U is equals to 10, 0.1, 0, and 0, 0.1. Okay, and R is also 1. This is the measurement. This is the process. Okay, these parameters can be changed, and so we need to learn about the number of state dimensions in here. N is equals to the what? The length of x true. Okay, because these are our initial condition, but it's in the form of the 2 times 1 vector, and so the R state space or the dimension of these values is equals to the what? Is equals to the n. Also, we need to give the what? The number of measurement. M is equals to 1, which means that we measuring only position in the system, and so we will estimate to the what? To the velocity of the R model based on this information. This is the hard one, and also we can measure the what? 2 values of these times, right? The n, position and velocity can be measured, but in this case we measure only to what? To position, and so we will derive to the what? To the velocity value based on the position one. Okay, so UKF parameters can be given with the what? The alpha 1 minus e over 3 minus 3, so the kappa is assigned to 0, and beta is the Gaussian distribution Q, and the lambda value can be calculated with what? Alpha over 2 times n plus kappa minus n. Okay, so after that we need to calculate the weights for this point, sigma points. Okay, so Vm is equals to, just remember the formula, lambda divided by n plus lambda. Okay, this is for mean, and for the covariance we need to give the lambda divided by n plus lambda plus 1 minus alpha square plus beta. Okay, this is for covariance. Okay, so After that, we need to build the what ei1 and up to 2 times n, because we need to build what the upper and the lower boundary conditions in here. And so the vm is equals to the what vm dot comma, which means that we can create the row values in here just like this one, and so 1 divided by 2 times n plus lambda. Okay, these are the basic notation about this code. And so also we need to give the what the vc value just like this one, and so this is the same. Okay, these are the algorithms for the what for initialization of the weights, the sigma points in here. Okay, so we need to allocate the space for estimates. We need to cap it in this position, xs the estimation value or the hat value, the zeros, and length t. Okay, and p is covariance matrix I n. Okay, we initialize the covariance matrix. Initialize state covariance and also estimated state. After that, we need to also store true states and the measurements. Okay, x is store value, the zeros, and length of t. These are the vector, time vector, and so z is stored. This is the measurement storing zeros and length t. Just remember that the m is equal to the 1, which means that we only measure the what position of these values, and so this is the 1 times length t vector, this is the 2 times length t vector. Okay, and also we need to give the initial estimate for the x hat or the estimated values, and so we need to give the double dot 1 is equals to the what 1.5 and minus 0.5. Okay, this is the initial guess. We can assign anything in here. So we need to build the simulation and UKF implementation in here. Okay, first of all we need to build to the what for k is equals to the 2, because it's in the form of the what forward difference equation, and so we can give to what to first of all true system simulation. Okay, but with process noise. So the forward Euler equation or the discretization can be assigned with what the x dot is a matrix in here, x true state, but with the 2 values, because it's the x dot, the velocity values, and so the mu also mu times 1 minus x a true position value, which is 1 over square, right, times x true 2. Okay, and minus x true 1. This is the nonlinear system for a given what for a given our van der Pol equation. And so how we can apply the forward Euler difference equation? X true value is assigned with what x true, right, plus x dot is the r continuous equation times dt plus mvn multiplied random variable can be built with this one as a process noise. 0 and 0 is the r guess for what Gaussian process noise with the mean values of the 0 and q and transpose value times sqrt dt. These are the process noise. Okay, process noise. And also we need to store to the what to the k values in here, just like this one, x true, because it's the r noise implementation of these terms. After that we need to build what the measurement with the what with measurement noise. It's coming from the measuring this data, for example, the ADC unit or the what, the pressure sensor converting to the what, the digitization process, okay? And Z is equals to the what, the X through 1, because we only measure the what, the position values, okay? Plus SQRTR times rent and function, okay? Noise value. And Z store should be kept in here, just like this one, Z, okay? And so after that we need to build what, the UKF prediction step in here, okay? These are the basic UKF implementation of this code. First of all, we need to generate sigma points. And so key value sigma points is a function of this term xest estimation value hat k minus 1 comma p covariance matrix lambda and n should be given in here, just like this one. And so how we can implement this function of these terms, chi is equals to what, the sigma points x p lambda and n. And so just remember the R algorithm, which is derived on the what, on our written page. And so first of all we need to calculate the square root of n plus lambda times p value, right? And so the s can be calculated with the call function, which is equals to the what, the n plus a lambda times p, and also we can build as the lower formation in here, because it's just like the Gauss elimination as a Cholesky decomposition can be used in here, and so it's useful for our case. And so the initialize sigma point matrix can be given with what, the chi value, which is the zeros n 2 times n plus 1, okay? And so the chi first value is equals to the x, and so the for k 1 to n. And so we need to give the upper and boundary conditions. K plus 1 is equalized with the what, x plus s k, and also chi n plus k plus 1 x minus s k, okay? These are the basic algorithms to generate the what, the sigma points. So this returns to the what are the chi values in here, just like this one, okay? And so how we can use these values? This is the upper and the lower bound of the R algorithm. And so we need to propagate sigma points through process model, okay? The chi prat should be initialized with the what, the zeros values, n 2 times n plus 1, because we have the states and the upper and the boundary conditions. And so for I is equals to the 1 2 times n plus 1, and so we should give the what, the process model should be written in here. X dot is equals to the what, the chi 2i, right? And so mu times 1 minus chi 1i, right, is the position, and also chi 2i minus chi 1i, okay? And so the chi prat I value is equals to what, the chi double dot I plus x dot times dt, okay? So the nonlinear model is modeled just like this one in here, and so the chi can be built by using the base operation. And so we need to what? We need to predict state mean. Just like this one. X pred is equals to the chi pred times Wn, right? And so also we need to predict the state covariance. For example, in this case, the P pred is equals to the zeros n, set 2 times 2 matrices, and so the for I is equals to the 1, 2 times n plus 1, and the x is equals to the what? The chi pred double dot I minus x pred. Okay, and so P pred can be built with the what? The P pred plus WC I, just like the formula, times dx times dx transform. Okay, this is the covariance matrices. The whole of these terms is related to what? The prediction state, right? So how about the UKF update state? This is called to the what? Prediction step, and also we need to give the what? Also update state. Update. First of all, we need to propagate sigma points through measurement model. Z pred sigma values, the zeros, m, 2n plus 1, okay? So for I is equals to the 1 to 2n plus 1, and so Z pred sigma value, but I is equals to what? The chi pred 1 I, right? Because the Z is equals to the what? Only the position value, okay? After that, so we need to predict measurement mean. Z pred is equals to the Z pred sigma times Wm, okay? And after that, innovation covariance should be built with what? S zeros m, which is what? The 1 and 1 0 matrix in here, because we have only one measurement in here. For I, 1 to 2n plus 1, the Z is equals to the what? Z pred sigma I minus Z pred. It's the error. And so S is equals to S plus VC I times dz times dz transpose. Okay? And after that, S must be added with what? With the R measurement in here. Add measurement noise covariance in here. In this case, we have the 1 times 1 values in here because we just only measure the position. Okay. So after that, we need to give the cross covariance in here. Pxz is equals to what? The zeros and m for I 1 2n plus 1. Okay, and so these values, dx is equals to what? Chi pred I minus x pred, dz is equals to what? Z pred is sigma values I minus Z pred, and Pxz, the covariance Pxz plus Vc I value times dx times dz, because it's the cross covariance. Okay. After that, the Kalman gain is calculated with the what? With this one, k Pxz divided by s. Okay, And after that, if this is the Kalman gain, and so the update state estimate, just like this one, x est k is equals to the what? X spread plus k times z spread. Okay. And also we need to update to the what? The covariance matrices in here. Update covariance. Okay. P spread minus k times s times k transpose. Okay. These are the what? The UKF code for the prediction and the update state. After that, so we need to plot the results. Just like this one, the figure. Subplot 211. Okay. And so the plot is equals to t. X is store value 1 green, line white 1.5, and hold on should be given here. Okay. And also we need to copy these terms, the x est value, the blue line white these times, and also z store is equals to what? For example, the k, or estimation is the k, this is the blue. Okay. Next label time sec, y label position, and after all we need to give the legend value, the true position, estimated position, and the measured position. Okay. So just like this one, we need to give the second subplot in here related to the what? The velocity values. B green, okay, X, and so we don't have any z stored in here, just like this one, and so this is the velocity value. Okay. So this is this one, and this is the true velocity and estimated velocity. So if we have everything in right, and so if we run this code, and then we will have these values just like this one. Okay. So just see that under the measurement noise, estimated position, which is given in here just like this one, and so the true state values of these terms is given what is in this form, but the measured position, just see that measured position is given on this page. Okay. And so the true velocity and the estimated velocity values are given in this case. So what is wrong with this code? First of all, maybe we have the too many noises in here, just like this one. So we need to define a new data set, just like this one, 0.01 and 1. And so if I run this code and then see that there's too much noise in here, see, but the estimated position and the measured position is what is on the R graph, and so the R estimated velocity value is good. And so if I choose the different values in here, and so we have the nonlinear estimated position values, just like this one, and so the R nonlinear state is what is a straight line, and between the error values between the true position and the estimate position are close enough to each other. Okay. And also see that the true velocity and the estimated velocity value is matching with another signal. Okay. But if I choose to increase the process noise in here, and so the R generated from the measured position is broken, for example, is the 100 values in here, just like this one, this is too much noise, or too many values, for example. See, this is not the van der Pol equation, but the true position is given in here, but the measured position is the what is this state, and so the the estimated position is based on the what? The nonlinear dynamics, and so the R process is going to do what? Is going to do this one. And the true velocity values is what? Is not close enough to this one. Because the R van der Pol is not current, or the is not proved, or the is not cannot be used in this case, because this is not a van der Pol, because it's too much noise in here. First of all, we may increase the R values in here, and so just see that the whole of these things are the noises. Okay, so how we can collect the or estimate the or to what? To interpret these results. First of all, we have too many noises in this signal, just like this one, and so the process noise is similar, or the white thing here. Just see that the R noise breaks the R algorithm. Just see the position is deflected with what? The minus 20 to 20. This is too high values in here, and so if I decrease, or no, if I decrease the R values in here, and so the R positions, the blue line, is what? The measurement error, -3 to 1, which means that the R system is going to do what? 1 meter to the -3. This is too much value for this estimation. And so if this is the case, and then the R can be set the 0.1, and so just see that this close to the what? The real-time measurement system model. Okay, and so the true velocity and the estimated velocity is good enough in here, but just see that R true position, green line, with match with the what? With the dot, the straight line, black line, which is the estimated position. This is matching with the what? With these noises in the extended Kalman filter, or in the normal Kalman filter, we cannot have these results based on this information. This is a huge advantage for the what? For implementation of the UKF filter on the what? On the Matlab. And so, if you are building with the what? With the real-time implementation, you just need to use the what? To these two prediction step and the update state. You can write this code entirely on the what? On your C++ code. On the what? On the STM or the TI development kit. Okay? The microcontroller. Okay? So this is how we can implement the what? The UKF filter on this nomination, just like this one. In the next lesson, we will talk about another example session about the UKF.